This is the penultimate week of our OCSP summer program, and I'm quite excited for it to be over very soon because you guys apparently have worked so hard to get to this point, and you probably need some time to take a break. I don't know when the semester is going to start, but from what I heard, Cornell's going to have some sort of a hybrid class taking structure, and I'm interested in seeing how that's going to turn out. Anyway, enough of my blabbering. It seems that some people are here and we're still missing a lot, but I'm just going to get started today. You're at the point of organic chemistry where you're just bombarded with all kinds of random reactions. And I think that's an unfortunate part of the organic chemistry education, and it's been taught this way for decades, and there's nothing much that I could do about it. So I'm just going to try to make it as not painful as possible. So we're going to cover a lot of reactions today. Hopefully you can feel free to ask me questions if you have any. You can also send me private messages, and I will stay after the lecture to answer any questions that you might have. Okay, let me flip my camera, because this way you would not be able to see anything I write on here. Oh. Sorry, guys. Video setting, and not near my video. There they go. Okay, cool. So, first thing we're going to talk about is more reactions with alcohol. So I'm just going to start writing reactions down on the board, and feel free to copy them down. If not, you can come back and rewatch the video so that you can, I don't know, recopy your notes if that helps you learn. Okay, so reactions with alcohol. Reactions with... The first thing I'm going to talk about is this very interesting and incredibly toxic chemical that is called thionyl chloride. So here's what it looks like. It has a sulfur, double bonded to an oxygen, and it looks kind of like DMSO, but that's not what I'm drawing here. For DMSO, there are two methyl groups coming off of the sulfur, but for thionyl chloride, we have two chlorines coming off of the sulfur, and that's our thionyl chloride. And it is pretty bad because if you see the structure of the thionyl chloride, there's the very electronegative oxygen double bonded to sulfide, and there are two very electronegative halogens single bonded to the sulfide. And what it means is that this sulfur is incredibly positive, and if you threw it anywhere with electrons, it's going to react. And I bet it smells bad too because it has sulfur in it. Anyway, so the reaction I'm going to talk about is this. I'm going to mark the stereal center like this because this is important for us determining the product. Sulfonyl chloride. And the solvent would be pyridine. So that's my shorthand for pyridine. If you don't remember what it looks like, I'm going to draw it out for you. Basically, you have a benzene ring, but for one of the carbons, you change that to a nitrogen. That would be pyridine. Okay, so what happens in pyridine? You're going to get a complete inversion of the stereocenter, and you're going to switch the OH group to the Cl group. And you're also going to produce a very toxic gas, and that's just going to go away. This reaction happens very rarely for a reason that I just talked about. The sulfur is incredibly electron positive. Also, the driving force for this reaction is the generation of the SO2 gas. Okay, so you've noticed that there's this stereochemical inversion. What does that tell you about the mechanism for this reaction? Can you take a guess?
SN2.
It might be an SN2 type reaction. Thank you, Nestor. Yes, the last step for this reaction is an SN2 type mechanism. So I'm going to talk about the entire mechanism now. And if you have any questions, if I'm talking nonsense, please just shout it out and let me know. Okay, so assuming you've all copied down the overall reaction that happens, okay, this is what we're going to do. My starting material, which is a very simple alcohol with a stereo center. I'm going to draw my thionyl chloride. We've already said that the sulfur in the middle is incredibly electron positive. What do you think might happen if we feed it with the alcohol in which there's an oxygen with lone pairs? Just going to sit here until somebody talks.
It wouldn't be positive anymore.
I'm sorry?
It wouldn't be positive anymore.
What would be positive? Sorry.
Oh, the sulfur wouldn't be positive.
It's not exactly positive. It does not have a charge, but it's going to be very partial positive due to all the electronegative things that are attached to it. So you have lone pairs here and a partial positive here. What do you think is going to happen?
The oxygen attacks the sulfur.
You're absolutely right. The oxygen is going to go after the sulfur because why not? Okay, going after the sulfur. Is that the end of this step? How many bonds does our sulfur have now? I count 5. Do you think it's happy? Probably not. Somebody's shaking their head. So what's going to happen is that one of the double bonds between the sulfur and oxygen is going to break, and you push one pair of electrons onto the oxygen. And oxygen will very gladly take that pair of electrons because it is incredibly electronegative. So what's going to end up happening is that we're going to generate a species that looks a little bit complicated. I have my oxygen here, still have my H attached, and here I'm going to have my sulfonyl chloride attached to my oxygen. And the top oxygen has a negative charge because, remember, we pushed one of the double bonds onto that top oxygen. So what's going to happen next? This is nowhere near the product. It does not look anything like the product. So what are we going to do next? Take a guess.
Will chlorine come off?
The chlorine will come off. That's absolutely correct. One of the chlorines will leave. But how is it going to leave? Is it going to leave on its own, or somebody would have to kick it off? Do we have anything that could possibly kick away a chlorine?
The negative charge on the oxygen.
Thank you, Alex. That is very correct. Okay, so the choice that we faced just now was that whether or not the chlorine was going to leave on its own, or whether or not something's going to kick it away. So my argument for chlorine not leaving on its own would be that now our sulfur has a full octet. It has 8 electrons around it, and it's relatively happy. Imagine the chlorine leaving on its own. How many electrons will we have left on the sulfur? If I break this bond. Now, how many electrons do I have around the sulfur?
7.
You would have, why would that be 7?
Oh, wait. And I just thought like chlorine would just take away 1 electron, and the sulfur would just get its 1 electron back.
That is a very important point because you're talking about a homolytic cleavage, which is not exactly what I'm referring to here, but that's a very good point. So by breaking that bond, I meant that the chlorine is going to take both electrons and just leave as a chlorine minus. So
Okay.
if that occurs, how many electrons are there around the sulfur?
6.
You would have 6,
Mhm.
which is less than the octet, which means that the sulfur is going to be very pissed off. So that's probably not what's going to happen. So as Lizette suggested just now, a more plausible way for the chlorine to leave is for us to bring down the lone pair and then kick it off. So what's going to happen? The resulting structure is going to look like this. You can try to draw it on your own, and then later we can compare what we have. Now we have a Cl minus just swimming around. I hope you can still see it. Maybe not. Yep, there we go. So, are we getting anywhere close to our product? Probably a little closer. So at this point, we have this gigantic group that's coming out of the board, and we have a Cl minus that's swimming around. What can we do to get to the product at this point?
Would the CO like try to bond with the hydrogen so that the hydrogen could leave?
Cl with a Cl bond with the hydrogen. You're
Yeah.
talking about this one.
Yeah.
It could. You're absolutely right. However, would that lead to our product?
No.
Probably not, right? So that process definitely is going to happen. And what it does is that it's going to be in equilibrium with this. However, this does not look like our product at all. You still have this giant group attached to our stereogenic center. So, it's not a really productive step to move forward. What can we do to make the next step productive and just get to the product? Anybody take a guess?
Maybe the chlorine would do a backside attack.
Yes, the chlorine would do a backside attack. And what would happen when it does that? Well, we're going to get a complete inversion of the stereocenter. Now our bond is coming out. When chlorine does a backside attack, it's going to come in from behind. And what's going to form is this side product, as well as, what else did we kick off? Right, we have this side product as well as this purity. That's the solvent that is just swimming around. So we've already got to my product, which is awesome. However, this reaction does not stop there. If you remember, what I drew in the initial full reaction was that the side product would be SO2 gas. Here we don't have SO2 gas. How would that happen? Well, the pyridine is also a base. It is not a super strong base, but because it has a lone pair on the nitrogen, it is a pretty decent base. And here we have an OH. An H attached to an oxygen is acidic or basic.
Basic.
It's basic. How? Can you elaborate on that?
Well, I mean, I just thought, if there's an OH, that's going to be a strong base.
If that, okay, so you were talking about this. If there's an OH, it will be a strong base. That's what we're talking about, the OH minus. You're absolutely right. That would be a. However, here we're talking about an OH group, which is hydroxyl in an organic molecule. And remember from a previous lecture I talked about hydrogen bonding, in which a hydrogen attached to a very electronegative atom could bond with other electronegative atoms. And because this oxygen is so electronegative, where do you think the electron density will be in this OH bond? Is it going to be closer to the H? Is it going to be closer to the O?
The O.
It's going to be closer to the O because it's more electronegative. You're absolutely right. So would it be easy for us to just remove this electron, this hydrogen?
Yeah.
It would be pretty easy for us to remove the hydrogen, right? So we're going to remove this hydrogen as H plus or H minus. Electron density is closer to the oxygen, which gives the H a partial positive or partial negative.
Positive.
Partial positive. Thank you, Manuela. Therefore, we're going to remove this H as an H plus. We have a pretty decent base. We have an H plus. What's going to end up happening is that our base, which I will denote as B minus, is going to come in, grab my proton. The proton is going to just relinquish all of its electron density. So we're going to form an oxygen-sulfur double bond. And at this point, we're exceeding the octet rule. So the chlorine must go. What we're going to end up producing is going to be the conjugate acid of the base, as well as SO2 gas, plus the chlorine that is just swimming around. And the conjugate acid of the base and the chlorine are going to be associated with each other because one of them has a positive charge and the other one has a negative charge. So that's how the entire reaction goes. The generation of the side product is not exactly very important. If you just remember one thing from this reaction, that is the complete inversion of the stereocenter. And just pay attention in your homework problems. I believe there's one that does this type of chemistry, and also in your exams. The mechanism is kind of beyond the scope of this course, but it will definitely be brought up again during your actual organic chemistry course. So, I thought it would be useful to expose you to the mechanism at this point, especially the type of reactivity that the thionyl chloride demonstrates. The reaction always happens on the sulfur in the center due to its extreme electron poorness. Okay, any questions regarding this reaction and its mechanism?
Yeah, I have a question. Like for the first step with the double bond going back to the O, is
Yes.
it necessary to do that, or can we just jump to the second step?
That is a very good question. And I remember when I was an organic chemistry student, I asked the same question to my professor, and her answer was that the orbital overlap is not going to allow this type of SN2 reaction. And if you would like to talk more about this, we can definitely talk about it tomorrow during office hour or later after the class, but I cannot just give you a one-sentence explanation while talking about molecular orbital theory.
Okay.
Okay?
Yeah.
Cool.
Thank you.
Yeah, so just remember, it might seem plausible to just let it kick away the chlorine, but no. It has something to do with the molecular orbital overlap, which we're not going to cover during this lecture. Okay.
Okay.
So more questions regarding the mechanism and the overall reaction? It's a nasty reaction to do, and I would not personally want to do it, ever, in my research lab.
I have a question real quick.
Yes.
Where did the B come from? I don't think.
Oh, the B is just purity. I didn't want to draw it again, so I just handed it as B. But, it's the same thing as purity. Pyridine is a pretty decent base, and it smells terrible, and it's a reproductive hazard. So don't ever try to smell it. Just take my information as a given. It smells like rotten fish. So, yeah, just so you know. Also, next thing in the textbook that I should cover is the assignment of oxidation number. That part I'm not going to cover today because you can just go to your textbook and read chapter 10.6. That's not essential to doing the homework, but it will be on the exam. And it should be very straightforward. There are, very explicit steps that you can follow, just like learning nomenclature. So I'm not going to waste time talking about it, but if you have any questions at all, you're more than welcome to come to my office hour tomorrow and we can go over how to assign oxidation number. But make sure you go over this because it's going to be on the exam. All right, so continue with alcohol. I'm going to speed up a little bit because I spent the first 20 minutes talking about the first reaction. So now we're going to talk about oxidation. There are two kinds of oxidations that we can do with alcohol. The first kind of oxidation is pretty mild. We're not going to drive it all the way to the most oxidized form possible. What do I mean by that? Well, we're going to go from alcohol to ketones and aldehydes first. Okay, so I'm not going to go over a mechanism for any of these reactions because you don't need to know them at this point. I'm just going to show you a bunch of reactions, and I want to demonstrate how certain oxidants can only do certain types of oxidation. So, reaction number one, we're going to have a very generic alcohol, which I've been using for the past 20 minutes. And I'm going to show you a reagent that looks very nasty. 2 sodiums, 2 chromiums, and 7 oxygens. How can you tell that it's an oxidant? Well, first of all, it has 7 oxygens in it. It's very incredibly oxidizing, literally. And what's going to happen to our alcohol? Well, it depends on what kind of alcohol it is. So now, what type of alcohol is it? Is it primary, secondary, or tertiary?
Secondary.
It is a secondary alcohol. I'm going to write a 2 and a little circle. I'm going to throw in just a little bit of aqueous acid as a catalyst. It's a secondary alcohol. What's going to end up happening is that instead of having an OH, I'm going to end up with an O double bonded to this secondary carbon. So that's what happens when you oxidize a secondary alcohol with a chromium reagent. We're going to go from an alcohol to a ketone. However, if we start with the primary alcohol, which I'm going to draw as this, and we're going to feed it with the same exact reagent, Na2Cr2O7, a bunch of acid to catalyze this reaction. What's going to end up happening is that we're going to get an aldehyde. Instead of having our group sticking off like this, we're going to end up having an extra hydrogen. So I'm going to write aldehyde. Okay. The reaction does not stop here. So every time when you see this reagent, be very careful, because if you have aqueous solution, it means that the reaction is going to go all the way to the acid. So here's the hierarchy. Alcohol is the least oxidized form with an oxygen. And then we can go higher to aldehyde or ketone. Double bonded oxygen to carbon. So, initially we start with 1 carbon oxygen bond. Now we have 2 carbon oxygen bonds, but it doesn't stop there. it's going to go all the way to the carboxylic acid. If you remember what carboxylic acid looks like, here it is. We have one oxygen double bonded to this carbon, but that's not enough. We're going to add an extra oxygen to this carbon. So you have 2 oxygens on that carbon, which means that your carbon is incredibly oxidized. And it cannot go even further without becoming something that's just a per acid, which we're not going to cover in this class. So we can go from alcohol to aldehyde ketone, but if the oxidant is strong enough, we're going to go all the way to the acid. So in this case, a chromium reagent is incredibly powerful. So we're not going to stop at the aldehyde. We're going to go all the way to a carboxylic acid. Some of you might be thinking, well, this is pretty bad because what if I just want to stop at the aldehyde? I don't want the acid. Well, people figured out a bunch of ways to oxidize alcohols with milder reagents. So once you're done copying these, I'm going to give you a few examples of mild oxidation. Actually, just one example of very mild oxidation. One thing to keep in mind, there are a variety of chromium ions that can do this type of very aggressive oxidation. And I want to list them so that in the future, when you see them, you know that the reaction, if it's the reaction with the primary alcohol, it will go all the way to the acid. So here are a few ions or molecules that I would like you to keep in mind because they're incredibly aggressive. We have the chromate ion, CrO4 2-. We have the dichromate ion, Cr2O7 2-, which is what we've been using, sodium dichromase. Also, we have chromium trioxide, which is a molecule. So once you see chromium in your oxidant, know that for a secondary alcohol, it goes to the ketone because it can't go any further. However, with a primary alcohol, you're going to go to the aldehyde and then the acid. Okay, so we want to be aggressive, we use chromium. However, if we want to stop at the aldehyde, we're going to want to switch to a different type of oxidant that is called PCC. I'll show you what it looks like. Just a second. PCC oxidation. It looks like this. We have a chromium trioxide, but it's not the only thing. We're going to add a pyridine to it and then an HCl to it. So just know that this is what PCC looks like, but during your exam or when you're doing homework, you don't have to draw this. Just write PCC, it will be enough and everybody knows what it means. So that is PCC. And PCC oxidation is mild enough so that we don't have to worry about the reaction going all the way to the acid. So I have PCC, and the solvent for this is typically methylene chloride, CH2Cl2. What I'm going to end up getting would be just the aldehyde version of it. Again, you will learn the actual mechanism for PCC oxidation in the actual organic chemistry class, and now we're just exposing you to this type of reaction so that you know the difference. Any questions regarding alcohol oxidation? Because if not, I'm going to switch to a completely different class of reactions. Okay. Doesn't seem like people have questions. Oh, somebody said something?
Could you repeat this one more time with the PCC oxidation?
Yes, absolutely. So PCC reagent is not just some very aggressive chromium reagent. With the pyridine and HCl in there, PCC actually is much milder than the ions that I just talked to you about. So PCC oxidizes primary alcohols to aldehydes, and it stops there. Unlike other chromium ions or chromium molecules, it does not go all the way to the carboxylic acid. So if you're given the choice between the PCC and other chromium ions, and you know that you want to get an aldehyde, do not use the other chromium ions. PCC is the way to go because it's much softer.
Is it only PCC or PCC and DMP?
PCC and what? Sorry?
DMP, I believe.
NMP?
No, the other thing the other weak oxidant that we got, I think DMP.
DMP. Are you referring to, which chemical are you referring to?
Hold up. I don't know. Never mind.
It's okay. So we can definitely talk about that. Let me make a note. DMP. There are definitely other milder oxidants. It's just PCC is within the scope of this class. I don't recall the professor teaching DMP oxidation, but we can definitely talk about it
Okay.
later in like after class, because I'm going to end early. It's not going to take that much longer for me to go through all those other reactions. So, all right, we can definitely talk about DMP. Just remind me after lecture because I might forget. I have really terrible short-term memory. All right, so no more questions regarding oxidation of alcohol oxidants? If not, I'm going to move on to a new class of chemicals. They're no longer called alcohol. They look kind of similar. I'm going to make some distinctions between a couple classes of compounds. What is this? What do you call this kind of thing? If it looks like this, what do you call it? Is it an alcohol? Is it an acid? Is it, I don't know. Somebody please say something, or I'm just going to sit here and get bored.
Is it an oxide?
It is very close. You're jumping one step ahead, but thank you for saying something. So this is actually an ether. But I don't know if everybody caught the word that she just said. She said epoxide. What does an epoxide mean? Well, imagine tethering those two R groups together. We're going to end up with something that looks like this, and with a bunch of R's sticking out. And this is an epoxide. Epoxide is basically a cyclic ether, but it cannot just be any cyclic ether. It has to be a 3-membered ring. So if you have a ring that's bigger, for example, we have dioxane. It is a cyclic ether, but it's not an epoxide. An epoxide has to look like this. You have a triangle and have a bunch of R groups sticking out. Okay, so that was a distinction that I was trying to make. So epoxides, they're ethers, and they're very prone to nucleophilic substitution reactions. So once they react, they will most likely open up. We call those type of reactions ring opening reactions. And today I'm going to talk about 2 types of ring opening reactions that are most common. The first type is ring opening under basic conditions. Let me just say basic. Okay, so I'm going to draw a very generic epoxide, an example I use all the time. That's my epoxide. And then I'm going to give you the reaction conditions. sodium ethoxide and ETOH, which is ethanol. And I'm going to heat it up to 80 degrees Celsius. That's pretty hot. That's probably reflux when the ethanol just starts boiling. And what I'm going to end up getting is that I'm going to open up the ring. So this carbon right here is going to be attached to an OH, and my OET is going on to this carbon. And my side product would be NaOET. Basically, I regenerated my starting material. Okay, so how does that reaction happen? Remember initially I said that this type of reaction, the epoxides are very prone to nucleophilic substitution. So it means that they follows an SN type mechanism. It doesn't matter if it's SN1 or SN2, we're going to talk about it. Okay, so the mechanism goes like this. Does this molecule look very comfortable to you? By being comfortable, I mean being stable, not wanting to react. We have a very small triangle of molecule. Have you seen a lot of three-membered rings? Some people are shaking their heads. No, we haven't seen very many three-membered rings for just one reason. It's because there are not a lot of them. And why is there not a lot of them? Because they're not stable. They would love to react. And the reason is that a three-membered ring is incredibly strained. By strained, I mean you gotta bend the bonds. If you had a model kit, try making a three-membered ring. You would have to end up with really bent bonds. So we have ring strain. That makes it reactive. We also have this oxygen, which is electronegative. If that oxygen is electronegative, it must mean that those carbons that form the base of the triangle must be partial positive. So once they see electron density, they will want to react with the electron density, and that's exactly what happens here. So I have my epoxide. It has a lot of ring strain, and it has partial positive carbons. And I have my OET minus, which is a charged good nucleophile. What's going to happen is that my OET is going to come and start an SN2 type of attack. And in the end, my ring breaks. I'm going to end up getting an oxygen with a negative charge and OET attached to the carbon that it just attacked. So where do I get this oxygen from? Hydrogen from? Well, remember we're swimming in a sea of ETOH, which is ethanol. We can just steal the hydrogen from the ethanol and get to our final product. I want to emphasize the regioselectivity as well as stereoselectivity for this type of reaction, and I want to make the distinction between the two. So regioselectivity means where the attack happens. It means that whether or not I attack this carbon or this carbon with more substituents on it. So for basic condition reactions, we're going to end up attacking the carbon that's less substituted, because this is a very similar reaction to SN2 type reaction, where less substituted carbon is typically attacked due to the lack of steric interactions. So under this condition, we're going to attack less substituted carbon. And for stereochemistry, we're going to have inversion of stereocenter. So that's for the basic conditions. And I want to emphasize that because once we switch to acidic conditions, the regioselectivity is going to become reversed, which I will talk about in just a minute. I'm just waiting for most people to finish copying and we can move on. Any questions regarding ring opening under basic conditions? Okay, since there are no questions, I'm going to move on to ring opening under acidic conditions, which is going to give us a complete flip of regioselectivity. Okay. Going to leave something on my board so I don't have to redraw it. Okay. Instead of ethanol, I'm just going to have an aqueous solution of some sort of acid. And this is only catalytic amount. By catalytic amount, I mean just a tiny bit, just a trace amount of it. We don't need one equivalent of it, just a tiny bit to get it started. Okay, so here, and we're going to use methanol. It can still be ethanol. It doesn't really matter. I just like methanol better for this reaction. Okay, so what's going to end up happening is that we're going to have the exact opposite product. No, there's no NaOET, which it was base. Sorry about that. Note that I erased the NaOET because it's a base. And now we have methanol as the attacker and the acid as the catalyst, which kicks off the reaction. Okay, so our product is reversed. Remember, initially, under basic conditions, our OR group ended up here, right? We initially had OET on the bottom and OH on top. But for this reaction, everybody is reversed. We now have the OR on top and the OH on the bottom. And this is how the mechanism goes. I'm under acidic conditions. The first thing that's going to happen is that I'm going to have a proton transfer, which is going to get me protonated. I'm going to have a positive charge on here. So how is protonation going to affect which side the nucleophile attacks? Well, let's focus on this OH for a little bit. Is OH a good leaving group? I mean OH, not OH minus, it's OH plus. Once it leaves as OH, a neutral species. Is it a good leaving group? It's a pretty good leaving group. Somebody is nodding their head. Thank you for nodding your head. It is a pretty good leaving group, which means that this bond here between the carbon and the oxygen is very weak because my OH is, you know, super ready to go at this point. So this bond here, I'm going to draw more clearly. It's going to, you know, already be very weak. We can almost think of this center as a carbocation. It is not exactly a carbocation, but we can think of it as one because this bond is so incredibly weak. So we have the formation of a carbocation, and we have methanol, which is a not so great nucleophile, but it can get the job done. So we have methanol right here. And the methanol is going to come in and add itself to the carbocation and then kick off the OH completely. That's going to give us the final product that looks like this. So what type of reaction might this be? Is it an SN2 type mechanism? Is it more like SN2 or more like SN1?
SN1.
It is more like an SN1 type of mechanism. You're absolutely correct. However, officially, there is still the inversion of the stereocenter because we do not formally form a carbocation. It's more similar to SN1, but it's still an SN type reaction, SN2 type reaction. So we're going to keep the inversion of the stereocenter, but here for regiochemistry, see how we just attacked the carbon with more substituents? Well, that's because the carbon with more substituents is going to be more stable. Imagine this as almost a carbocation. This carbon center is going to be more stable than that one. Therefore, it's more readily formed and more readily acceptable for the attack. So I'm going to erase the less substitute carbon and say the complete reverse. Regiochemistry-wise, we're going to attack the more substituted carbon under acidic conditions. And when you take the actual organic chemistry course, your professor will definitely emphasize this point because it's very easily forgotten after you've learned hundreds of other reactions. Hopefully you retain this bit of information when you enter the new semester. Okay, any questions regarding the epoxide chemistry?
So this was an SN2.
Sorry, what was an SN2?
You said this is an SN2 reaction?
Yes, it's an SN2 type reaction.
It just still confuses me how it's SN2 if we have like a kind of like a tertiary carbocation.
Yes, so that was misleading on my
Like,
so this is not exactly a carbocation. It looks like a carbocation. So this bond is very, but it's still there. So this bond is not going to completely break until we have the methanol attack this carbon. So it's a very strange reaction. It is an SN2 type of reaction that looks like an SN1 reaction.
Okay.
So we have to use SN1 type reaction mechanism to explain its selectivity. However, it is officially an SN2 reaction for which you have inversion of stereocenter. So both for acidic and basic conditions, we have inversion of stereocenter. It's just their regioselectivity are completely opposite.
And
Right.
is the MEH the solvent?
The MUH is also the solvent. You're absolutely correct.
I don't know. That just like because isn't MEOH a polar protic solvent?
It's a polar protic solvent. You're absolutely correct.
So wouldn't that mean like it favors like an SN1E1?
So how would I explain this? When we determine what type of reaction it is, and we're not just going to look at the solvent would make the reaction prone to SN1E1 reaction. However, and also this reaction looks like an SN1 reaction, but it is officially an SN2 type reaction. So we gotta consider all of the factors. It's not just the solvent. That's why this topic is so difficult and confusing. Sometimes we cannot even predict it, and we just have to do the experiments in order to find out which type of reaction it is, and then retrospectively justify it. Okay, sound good? Okay, cool. So last three reactions I'm going to talk about are incredibly simple, but I do have to deliver the information to you, and then hopefully I will only take about 5 minutes to blow through those three reactions. And then I will leave some time for questions, and if you don't have any questions, I will wish you a very happy weekend, even though it's only Wednesday. Okay, so I'm going to talk about sulfide a little bit. What are sulfides? Well, sulfides have the formula as RSH. R group, sulfur in the middle, and an H on the side. How do we synthesize? So a bunch of, let me backtrack a little bit. We also have RSR, which is
which is a which is thioether. So the difference between thioether and ether is that for an ether, you have an oxygen in the middle, but for a thioether, you have a sulfur. So everything, they're pretty much very similar. It's just that we substitute oxygen with a sulfur, and we therefore have to add the prefix thiol to it. It's a thioether. Okay, so how do we make thioether from a sulfide? Well, so this reaction, incredibly simple. Still gonna talk about it. We have an alkyl bromide. I'm going to get sulfide. What do you think is gonna happen? I'll show you the product. What do you think happens here that leads to this product? Okay. It's pretty much just a very simple SN2 type reaction. So that's how we go from sulfide to thioether. Very simple, but easy to forget. So that's just one way to make it. And we're going to end up getting HBr, which is hydrobromic acid, as a side product. This reaction is a very nasty reaction. First of all, sulfides smell terrible, terrible, terrible. I don't know if anybody has ever smelled rotten eggs. That's basically what sulfide smells like because of the sulfur. And also we generate HBr, which is an incredibly strong acid, and don't ever dip your fingers in the fume. Even the fume can burn you pretty badly. Okay, so this is the thioether synthesis that I threatened to talk about. Any questions regarding this synthesis? Okay, so 2 more reactions I'm going to throw out here. Number 1, got SH, NaH, give you a generic ether. Well, first step, NaH is a very interesting molecule because the H is not an H+, it is an H-. You can figure that out by looking at the counter ion. We have sodium plus, then H must be a minus. So what does that do? Well, see, we also have an H on the sulfur, and sulfur is electronegative, which means, is the H negative H or positive H?
Positive.
It has to be a positive H. So we have a negative H and a positive H. What do you think the H's are going to do?
Like bond with each other?
They're going to bond with each other. Thank you. And form what? Just put them together. What do you get?
Hydrogen gas.
You're going to have hydrogen gas evolution.
Oh, okay.
Hydrogen gas. Yes, I understand. That was not a trick question. Okay, so we're going to form hydrogen gas, and this ion, that is not going to just stay there and not react because we also have ether in there. So what's going to happen is that it's going to come in, attack this electron poor carbon, kick off this ether, and we're going to end up with a thioether, as well as this OR minus ion, which will coordinate to the sodium spectator ion. And that's it. That's a pretty simple SN2 type reaction. And one last reaction I'm going to talk about is incredibly similar to this. So we're also going to use the NaH to generate hydrogen gas and free our S- ion. And then, instead of using an ether, I'm going to give you some sort of alkyl bromide with very specific stereochemistry. So what's going to happen here? What do you think is going to happen? Apply the knowledge that you just heard about. Okay, nobody's willing to talk. That's fine. I'll talk. It's my job anyway. All right. So we're just going to have a very simple SN2 type reaction, just like the one that we just talked about. And we're going to have a complete inversion of this bond, a stereocenter. That was a terrible looking bond. Complete inversion of the stereocenter. And we're going to have NaBr precipitate out as a salt. All right, so those were the two last reactions I planned for today, and we have 4 minutes left. I'm going to open the floor to any questions you might have. If you don't have questions, feel free to just sign out. If you have questions, I will be more than willing to, stay here and answer them.
I have a question on the thionyl chloride reaction.
Yes.
I kind of forgot what you said. Like, what causes the first Cl to be kicked off?
Let me draw that. I suck at describing things with words because English is hard. That is my thionyl chloride. I don't know if you can see it. Can you see it?
Yeah.
Okay, you can see it. Cool. So I am an alcohol. I'm just going to write ROH. Where does this lone pair go?
To the sulfur.
The sulfur. What's going to happen next?
It breaks a bond with the double O.
So what I'm going to end up getting is ROH S O minus Cl and Cl.
So what causes that chlorine to leave? Just because sulfur breaks the octet rule? Or
Because I bring down this lone pair, and my chlorine would have to go because I cannot break the octet rule.
Oh, okay. Thank you.
You're welcome. More questions?
So we can't just have the lone pairs of the oxygen like attack the sulfur and just kick off a chlorine. We have to go through like
Right.
that.
So I see what you're saying. Again, we're going back to Emanuela's question, whether or not we can just do an SN2 type reaction and just kick away the chlorine. So the answer to that, a short answer to that is we cannot, because let's consider the geometry of this sulfonyl chloride. What do you anticipate the geometry of the central sulfur to be? It's not a true question. I drew it on the board that way.
A trigonal planar.
So we have a trigonal plane, which means that my sulfur is completely flat on the board. So remember, when we do an SN2 type reaction, we have to do backside attack, right? So in order to do a backside attack, I would have a center and something coming out toward the front and something going back in. Let's say those are H's, and this is a BR. And I want to do SN2 type reaction. I cannot approach the molecule from the top or from the side. I have to approach the molecule from the back. And we then have a complete inversion of stereocenter. But here, we have a flat molecule. We cannot approach it from the front because this Cl is not in the bag. we cannot approach the CL from the back because the CL is not in the front. Can we approach the CL from the side? Well, we can't because there's nowhere for the CL to go. There's no orbital out there for the O to come in and kick away the CL. The geometry just doesn't work out.
Okay, that makes sense.
Great. Okay, any more questions?
Yeah, so when you were talking about the last three reactions,
Yes,
which ones had inversion of stereochemistry?
all of them.
Okay.
They're all SN2 reactions, therefore all of them have inversion of stereocenter. Okay.
Actually, do you mind like redrawing the very last reaction?
Yes, of course. Of course I can draw it. Let me just erase part of my board, and I had this NaH, and then Br. Step 1, treat it with NaH. I'm going to end up getting a negative sulfide ion, as well as H2 gas. Step 2, I'm going to just do a backside attack, kick away the bromine, and that would give me my product.
Okay, thank you. And I also have another question. Where you talked when you were doing the very first part of your lecture with the dianyl chloride.
Yes.
Were you saying something about like there being an inversion of stereochemistry?
Yes.
Can you like re-explain like what was?
Absolutely. Mm-hmm. So inversion of stereocenter happens towards the end. I'm going to like just show you the entire mechanism and emphasize the last step. So the mechanism goes like this. Okay, so we have our dianyl chloride. Again, we've seen the steps sometimes, many times. OH, I have my S, O, Cl, Cl. And my oxygen kicks off a chlorine. So what's going to end up happening is that we get this compound, well, this positive charge. And we have a Cl that's just free floating. At this point, my Cl is going to initiate a backside attack and kick off this entire leaving group. And what I'm going to get is inverted stereocenter plus this HOS blah thing. So that's where the inversion comes from.
Okay, thank you.
You're welcome. All right, if you guys have no more questions, I wish you a happy weekend. See you next week.